This is the video solution for questions 31 to 40. In question 33, heat is evolved, so it's an exothermic reaction, and the yield of the product. So we have to deal with temperature and pressure. So now, because an exothermic reaction, you require lower temperatures for the forward reaction. As you can see, we have 3 moles of reactants giving you 2 moles of products. So if you want the number of moles, gaseous moles, to decrease, you have to increase pressure on the system. In question 35, the vapor density of N2O4 at a certain temperature is 30. Percentage dissociation is asked. So we write for the dissociation of N2O4. Vapor density is 30. Okay, so basically we have to deal with average molar masses, and while dealing with average, we can always take the initial moles as 1. At equilibrium, if this is 1 minus alpha, then this is 2 alpha. So the average molar mass would be total mass by total moles. Now total mass would be same as the initial mass because it would not change during the chemical reaction. The initial mass for 1 mole is 1 into molar mass of N2O4, which is 92, divided by the total number of moles, which is 1 plus alpha. Now this is given as 60 because average molar mass is twice of vapor density. So that gives you alpha. Okay. Question 36. As we have 2.5 gram in pure sample, okay, containing weak monoacidic base. So we have a base BOH, which is dissolved in 100 ml water. Okay, titrated with 0.5 mol HCl, and 1/5 of the base was neutralized. The neutralization reaction gives you salt plus water, and at equilibrium, when partial neutralization takes place, you'll be left with BOH and its salt, so you will have a basic buffer. Now let's say we start initially with 5x of this, and we have added x amount of HCl for 1/5 of the neutralization take place. So at equilibrium, we have 4x amount of BOH and x amount of PCl. So this basic buffer BOH can be written as pKb plus log of the salt or conjugate acid, which is B plus, divided by BOH. So that should give us the value of pKb. pH is given as 9, so POH would be 5. So the equation is 5 is equal to pKb plus log of 1 by 4. So pKb becomes 5 minus log of 1 by 4, or 5 plus log 4, which is 5.6. Okay, for the first part, we found out the value of pKb. It's 5.6. That's one of the questions which is asked, the value of Kb. The second question is concentration of salt at the equivalence point. Okay. Okay, so we had 100 ml of water to begin with, and we have 0.5 molar of HCl. Okay, there's one more information. It says at equivalence point, pH of the solution is 5. Now at equivalence point, BOH is completely used up and you only have BCl. At equivalence point, you only have BCl, and B plus undergoes cationic hydrolysis, which gives us pH of the solution. Because B plus itself is acidic, you can directly write the value of pH as half of pKa minus log C. This is the formula for a weak acid. pKa, however, has to be written as pKw minus of pKb minus of log C. And this is given to us. This is given as 4.5. So let's calculate the value of concentration from this. So this is 7 minus 2.8. Log C turns out to be 0.3. So C has to be sum of 2, right? Okay, let's test a minute. Log of C is minus 0.6. Oh, not bad. Minus 15. That's minus of 0.6. So that's 2 into 0.3. So this in fact gives us that C is equal to 1 by 4 molar. Okay, that's for the second part. Concentration of salt at equivalence point. The first is volume of HCl used at equivalence point and weight percentage of base in the sample. Now for volume of HCl used, I can use concentration of the salt which we just found out to calculate volume of HCl used. Okay, so we have 100 ml of water to begin with, and we do not know how much of HCl we have added. Let's say we have added V volume of HCl. So the amount of HCl which you add will also be equal to the amount of BCl which will be formed. The number of moles of HCl added is 0.5 into V. This is also equal to the number of moles of BCl formed. Now the concentration of the salt will be its number of moles divided by the volume. And total volume is 100 ml which is present initially plus V ml which you've taken as volume of HCl solution. This is given to us as 1 by 4. In fact, we just found this as 1 by 4. So you can use it to calculate the value of V. Once V is known, the number of moles of HCl will be known as 0.5 V, which would also be equal to the number of moles of BOH. Once you know the number of moles of BOH, you can multiply it with its molecular weight to get its total mass. That will give you its weight percentage as well. Right. Okay. Question 37 is a graph-based question. This is something which we've done directly in class. Just refer to the class notes for this. In question 38, we have titration curves. It's mainly asked which of them is smaller or greater, and if K2 is K1 plus K3 by 2. We can't say that. We can't say nothing. You see the initial same concentrations. Yeah, we have same concentrations of the three acids, and they have initial values of pH as 2, 4, and 6. This is less than 4, that's less than 6. We don't know the exact value, so I don't think we can say if it's K1 plus K3 by 2 or not. Yes. If the value of pH is less, then it has to be more acidic, which means the value of K1 has to be greater. So lower the value of initial pH, higher will be the value of K. So this is the condition which we have for this question. In question 40, forward reaction. This is a question on Lee Child's principle. If you introduce a inert gas at constant volume, if the volume is constant, then the equilibrium does not shift in any direction. If you add chlorine gas at constant volume, if more of chlorine is added, then the equilibrium will shift backwards. Won't be a forward reaction. Introducing an inert gas at constant pressure. If you introduce inert gas at constant pressure, the volume of the container has to increase. Partial pressures will decrease, and to negate that change, it will have to shift towards great number of moles. So this will give you a forward shift. If you introduce PCl5 at constant volume, then that also gives you a forward shift. That's it for